Hey everybody. So today I want to talk to you about diffusion across compute and involving geometry is how I want to frame that overall. And I want to start the discussion with this particular research paper, which is called Multi-View Diffusion Geometry Using Intertwined Diffusion Trajectories. And this research paper caught my eye, of course, because of the title. And then so when I look into it, look at this paper. This paper is a very unique paper, right? And I've seen this before, where essentially, so you just have a couple of names, no associated institutions with them whatsoever, and then they've submitted this research paper to this very obscure French research publication, and it's like everything about this research paper is made to make it obscure. Like the authors of this very purposefully wanted it to be obscure, as opposed to like the opposite, where it'll generally be like generally something more along the lines of like philosophy, and then it'll be one singular author with their institution associated. But within it, like there's like the key giveaways, like they submitted this to like this obscure French institution, like a publication, like very specifically, right? And then like they very specifically obscure the, like, I don't even know what association the authors are, because they have it like with an A and an asterisk, and then the asterisk doesn't actually point to anything, and then I would need to go deep into the appendix to figure out where that A is pointing to overall. But this paper is very interesting. The reason why I think they want to obscure it is the majority of this research paper is two algorithms. Algorithm number one is interesting. It's okay. It's diffusion maps for a single data view, and then so essentially it just allows you to create a diffusion map for one singular trajectory or one singular modality. And then what they do with algorithm 2 is the MDT based diffusion map. And then algorithm 2 is, you can see, there's a lot of this research paper, right? And then it's still going algorithm 2, and this is like the end of algorithm 2, and then this is the experiments within the two algorithms. So majority of this research paper is this second algorithm. And then the second algorithm is essentially joining multiple modalities of diffusion across time. What's a simpler way that I can put that into like actual human terms to understand would be like, so think of it like maps versus globes, and then looking at different map perspectives and or different globe perspectives. Right? And then so traditional method, what method A would be, like the standardized method would be that I take map A, B, and C and D, and then each one of these maps has let's say that it's the 14th century, right? Like it's like 1498, and then we're a map maker, and then we're making a map of the world, and then we take four different maps from four different map makers of the world, and those four maps are going to be different. Right? And then so how do we know which one of those maps is like the actual real map in 1498? We make an amalgamation of the four. We blend the four together, right? And that's typically the standard approach within this. Whereas with this algorithm, what it does is saying, rather than like just like take a blend of those four, take a viewpoint and a snapshot of the trajectory, right? So let's, instead of looking at the four maps, let's look at a map from 1495, 1496, 1497, and 1498. And then let's look at how those maps change. Like, what's the difference between 1495 and 1496? 1496, 1497, 7, 8, 8, and 9. And then let's build our map based off of what our deepening understanding is over time as that trajectory changes, right? And so it's a completely different way of amalgamating these maps. It's the same data, but it's utilizing it across multiple modalities, and that's what this whole research paper does, and it dives into. And then with this research paper, they do like, and they create some really cool and some pretty diagrams. Like it is the end result of this, right? And this is like data, like that's the shape of data. And then so the shape of data can be pretty cool, right? To me overall. And then also what they show within this too is that this method of essentially like temporal base, like temporal geometry, right? Like essentially measuring it over time, as opposed to like that amalgamation of like the fixed static geometries, is better overall, and it performs significantly better on their research overall. And then I want to take this a step further, because to me, like, this is a interesting paper and an interesting research paper, interesting hypothesis overall, but I can prove out their hypothesis one layer deeper, right? And then so within this research paper and the hypothesis of this research paper, they break this out into multi-modalities. But my argument for a long time, for a while, has been, and it's to me 100% proven out within this research paper before I dove into this, that the like modality aspect of it isn't important, right? And then what I mean by that, and I've showcased this a lot on this channel. Like I've made, like, I've talked about like the experiment of like encoding like a JPEG to a bird, and then I've made the video like this is not a picture of a cat, and then like things like that, right? Where it's like actually uh, uh, I've showcased that. Every video file has a embedded like audio geometry file associated with it, right? And then so all of these things to me paint this very clear picture that like modality is more of a human construct. Like modality doesn't, like multimodality in and of itself doesn't actually exist, right? Like for example, like we have like the ears, nose, and the throat, right? And then we consider a lot of multimodality fusion is based off of that and that concept, and thinking of that in general, and then trying to apply that, right? Like the ears, nose, and the throat. And that's always like, to me, like I'm not a doctor, I've never been a doctor. And then understanding, taking a base understanding of biology and then trying to apply that to like computation and computers, things like that. That concept of that fusion has always stood out to me and interested me, and I know it has with a lot of other like researchers in these areas, right? Which is why multimodality and multimodality fusion comes as like an important aspect of this, and which is like what all of this research centers around, is this multimodality fusion. But at the end of the day, like the multimodalities in and of themselves are more of a human construct to me. And then so meaning that like and in that instance, like the ears, nose, and throat would like yeah would be more of like a the differentiation between them is more of a human concept. They're just all the same region, same tunnels, right? And then so within that and within this, I ran some experiments to dive deeper into this, and essentially like my overall core thesis within that is that I could take this exact same research that they do within these multimodality views, and instead of utilizing multimodality as that fusion mechanism, I could utilize and can utilize just different measurements or different types of measurements and of the same exact data set, and that does the same thing as multimodality would. And then utilizing the same temporal math that they do in this research paper, I apply that across different data sets, and I apply this across 4 data sets. And then what I show is exactly what I hypothesized from the beginning, even more so within the data overall, is that the sum of the parts, like the measuring like 5 different data sets, is better overall than any one singular data set, which is important overall in this equation. It's like the exact opposite way that people typically dive into these things, right? And then so for years, I've argued that AI models and probably the human brain don't need more modalities to be intelligent. They don't need more sensors. They don't need bigger data sets. They don't need more views of the world. What they actually need is something much simpler: multiple geometric interpretations of the same data. Once you have that, you don't fuse them, you don't average them, you don't force them to agree, you move through them over time, like walking through different geometric lenses, and the underlying structure suddenly reveals itself. The idea is so simple that people tend to overlook it, and yet it's probably one of the most important truths about intelligence. This week, I decided to prove it, and here's what follows as a result. Multimetric diffusion, a new model of how intelligence actually works. So a new paper, the paper that we just discussed, multi-view diffusion geometry using intertwined diffusion trajectories, explored what happens when you run a diffusion process through different views of the same data. Think multiple sensors, multiple modalities, and multiple measurement systems. They found that if you alternate between these views over time, that the true structure of the data emerges more clearly than if you try to average the views or if you just picked one of the views. And then so my hypothesis takes this one step further. You don't need the multiple data views at all. You only need to measure the same data in different ways. So different distance measurements, different geometric assumptions, and different ways to compare points. Each one becomes its own view, and each one becomes its own observer, is the way that I want you to think of this. Each one creates its own diffusion operator, and a trajectory through these operators over time unlocks a structure that no single metric can detect. And then this is the deep part. Intelligence is what happens when you diffuse through multiple geometries, not when you fuse them, when you move through them. So let's test that. And then before we test that, this isn't a bold and important claim here, but to me it's backed up by this data and this research, right? And it's a concept I've talked about a lot on this channel before, which is when it comes to computation, like it's famous that like no one can actually like tell you what computation actually is, what like computer science actually is, right? There's a famous MIT lecture from the 1980s where he starts off the lecture and he says, this is you're going to find this class very interesting because this computer science class neither focuses on compute nor on science. And that's kind of true, right? Because no one can explain how compute actually works overall. And then so my explanation for compute and how it works overall is very simplistically that it's all a diffusion process, that everything breaks down to a diffusion process overall. And that this diffusion process, if you just measure it and you look at it the right way, essentially you get everything that could come out from intelligence via this diffusion process. And then so the experiment, one data set, many geometries. So to verify this hypothesis, I ran the exact same data set experiment on 4 different real data sets, all from classic machine learning benchmarks. I utilized digits, iris, wine, and breast cancer. And then for each data set, I built 4 distance-based geometries. Euclidean on standardized features, cosine on standardized features, Euclidean on PCA features, and Mahalanobis on standardized features. And I probably mispronounced that. I just want to call this out. Like I hate it when like anybody like they say like, oh, like you're completely discredited because you mispronounced this singular word that has like absolutely nothing to do directly with your theory overall, but because you obviously like you mispronounced this like like that is so. I mean. Don't ever watch my videos again if that's your philosophy overall, is my approach to that, right? And then so each metric creates a different geometric view of the same data. From each view, I built a diffusion operator, exactly like diffusion models, spectral clustering, or graph Laplacians do. Then I computed 3 baselines, the best single metric, the integrated operator, which is a simple average of the 4, and then random multimetric diffusion trajectories. So like walking through essentially the different modalities, and then or like the different measurement types, right? And then this last category is the entire hypothesis, that a diffusion trajectory through metrics will review more structure than any single metric alone or any naive combination of metrics. And the question being within that is, did I actually do that? And then so within this concept, like there's to me, all of this is based off of affirms and wouldn't be possible without relativity, right? This is all to me relativity. So like think of these different measurements, these different distance measurements as different relative observers, right? And that's the most simplistic way that I want you to think of that overall. And like so, we as humans currently exist on a massive spinning ball that is like rotating and moving around space at like we'll call it like 17,000 kilometers per hour, and then like the it's rotating around a giant circle that's even like massive multitudes bigger sphere than the Earth, that's rotating around the universe even faster than that 17,000 kilometers per hour, and then all of like the everything in the universe is just all of this like massive speeds of spinning, right? But to you, that's all like as the like observer, like you don't observe that, right? You don't observe any of that. Like you're more this Euclidean on standardized features. But if we were to take like the Hubble telescope or something like that could actually be measuring like on that, then they would have a different perspective as an observer than you would, right? And like just think of like that these different measurements in that same type of context. And so the results overall, I can break them down to you in the notebook, but overall, what we see is that with the digits data set, I'm able to improve it by almost 12%. So largest overall increase and improvement, and trajectory diffusion massively outperformed all other baselines. In the iris dataset, same thing, consistent improvements. Trajectory produces a much higher CH score overall, which means that it's we have like a structure clarity is much more apparent in the temporal trajectory method that I outlined there. With the wine data set, it was interesting, right? Because it's the base model scored 97.19, so it's kind of hard to improve upon that, but we were able to. So from 97.19 to 97.75, so even a data set that's already nearly separable improves under metric trajectories. And then breast cancer is like the biggest win to me overall, because so a baseline metric is 85, and then we get it to 92, and then so huge real world impact plus 7% absolute accuracy improvement, and then more than double the CH score. So this isn't a small effect. This is not data set dependent. This isn't lucky runs. This is a pattern all throughout, right? 4 different data sets all showing you improvement utilizing this method overall, which is essentially, again, just measuring the same data set utilizing different ways of measurement, and then combining those different ways of measurement in a unique way. And then so what this means is that intelligence emerges from moving through geometry. And then so let me explain it clearly and say it clearly, that different metrics give you different geometric realities. Like each one of those individual observers is it's their own different reality, right? And then so Euclidean tells you one kind of neighborhood, which is a completely different reality than cosine, which tells you another, which is a completely different reality than the Mahalanobis, which tells you a third, which is completely different than PCA, which tells you a fourth. Which again, going back to like that space analogy, you as an observer, your reality on Earth is completely different than an observer of a reality of someone that would be on Mars, which is completely different of a reality as an observer of like the Hubble telescope. And then so none of these is true, right? Like you can't say like the Hubble telescope's reality is true and all others are false. Each one is a perspective. And then fusing perspectives by averaging them destroys the very differences that make them useful. And so if you just take like okay, like we don't know, we'll just combine all of those and then smash them together and smush them together, and then people can't figure out like why that isn't very efficient with this data, right? But if you move through them over time, then something else happens. You get true structure that's reinforced across metrics, noise is canceled, artifacts do not survive across metrics, geometry becomes clear, clusters become sharper, semantics emerge, and accuracy improves. This is what the experiments proved across the data sets. And then so why this matters for AI and for brains too is that transformers already operate this way, but nobody acknowledges it. Like this is to me like the bottom line within this, right? Transformers accidentally do these things, and then you see, I don't know, you see like a lot of hate on transformers recently, and I've flip flopped a lot on transformers, overall, right? I'm in the camp that I don't think that transformers are the be all end all of what will get us from here to there. But I think that transformers are getting us a lot further and will continue to get us a lot further than even like prominent researchers want to recognize simply by accident. And but every attention head equals a different metric. Every layer equals a different geometry. The residual stream equals integrated metrics. The forward pass equals a trajectory of diffusion operators. KV cache equals temporal metrics, and layer stacking equals geometric time. And I think again, like none of these are like none of these mechanisms were built out to do these things. It's just that these were built out in order to make the transformer model work as it does, and architecture work as it does, and then coincidentally those align with these physics aspects with, and so it's without anyone knowing how computation actually works or worked, kind of just built it. And so your brain does this too, right? So V1 is Euclidean, and then you have the temporal cortex, which is sequential distances, and then you have the hippocampus, which is map-like distances, and then you have the prefrontal cortex, which is semantic distances. So you don't perceive one geometry, you perceive many sequentially over time, and then the movement between them is intelligence. That's what you are. It's what I am, right? And then so the takeaway from that is that the entire field has been obsessed with multimodality, as if intelligence requires more inputs, more sensors, more data sources. But the truth is simpler. If you measure the same data in enough different ways and diffuse through those measurements over time, you get the same benefits as multimodal perception without needing any of the new data at all. And then this is why, essentially, to me, the universe works. And then so now that we have hard evidence across multiple data sets to demonstrate it, if someone wants to publish this at like NeurIPS or ICLR or any like other like big publication institution, like this is, I'm giving you like this is what you would see at one of those big publication forums, right? So like feel free, perform a few more tests if you want, add a learn trajectory search instead of the random sequences, and you have like literally a paper that you could present to NeurIPS if you want. Personally, I'm not chasing academic validation. I'm too busy building the next architecture, and this to me overall is for people who understand what they're seeing, and then what exactly this is. To me, it's just proving out this is exactly how these things are working. This is why they're working, and then let's move forward from there. That's all. Like, I mean, to me, that's all it is at the end of the day, right? And so I'll leave a link to both the research paper as well as the Substack article here, which will then give you access to the code here that you can take a look at and review. And if you want to like call out, if you have any sort of like problems with my code overall, anything like that, any of my models, just be very direct with like exactly what your criticism is, right? Like I'm not like if you like you're just like have you run his code, like none of his models work, like I'm just gonna ban you from my channel, right? Like flat out. Like just calling it exactly how it is. I'm just not trying to deal with that overall. Like I don't care to debate you over that. If you want to debate over real stuff, let's go. But so I'll leave a link to all this, and if you want to debate it, I put in a lot of work in doing these, right? Like putting all this out there, and then so if you want to criticize it, I expect you to have a kind of the same kind of work and validation within that. Also, too, there's a lot of other places where like you could like post criticisms about me like nonchalantly if you would want, right? That aren't my channel. Like there's like 99.99999% of the universe that exists where you could do those things that aren't my channel. It's pretty simple overall. And then so if you like this type of content overall, please like and subscribe. Thank you very much.